Hello and welcome back to the Dementia Researcher Podcast. We're here again with the second of our 5 specially themed podcasts, sharing some of the narrated blogs we've published throughout the year. Just in case you're playing catch-up, I'm Adam Smith, I'm the Programme Director for Dementia Researcher at University College London, and I'm delighted to be introducing these special shows. This week, we'll be covering some careers advice, psychosocial research, exploring public engagement, and going back to the darker days of 2021 to explore some lessons from previous lockdowns and think about well-being and resilience. Today, we've selected 4 blogs which share some of the amazing knowledge in the heads of our bloggers who are based in the lab, exploring some of the science and biology. Our first blog comes from UCL-based colleague Dr. Christina Toomey. Christina works in the UCL Brain Bank, and in this fantastic blog, she shares some information on her own work and how the Brain Bank works.
How does a brain bank work? When asked what I do for a living, I say I'm a scientist, and most people are intrigued and want to know more. When I then say I have worked at a brain bank for the last 10 years, I get a range of reactions. Some don't know what that means. Yes, literally a bank of human brains. Some are fascinated and want to know exactly what a human brain is like, and many just make a comment that it makes their job sound boring. So what is a brain bank? Brain banks are precious collections of human post-mortem brain tissue that have very kindly been donated when somebody has passed away. There is a whole network of brain banks in the UK and throughout the world. This network allows coordinated methodology and tissue requests across many brain banks, meaning more consistency with how brain tissue can be used within the studies from multiple brain banks. By collecting the brain tissue, brain banks are able to provide a diagnosis to relatives and then use the brains in research projects to understand disorders that affect the brain and central nervous system. Brain banks specialise in different aspects or different nervous system disorders. Within the UK, brain bank networks, for example, are brain banks specialising in dementia, Parkinson's disease, multiple sclerosis, autism and sudden death. As a dementia researcher, I work at Queen Square Brain Bank for neurological disorders. We collect brains from a variety of Parkinsonian disorders as well as a range of dementias. During life, a patient will decide whether they want to donate their brain for research. They will provide informed consent and become a registered donor. At time of death, one of the brain bank administrators will be in touch with the family and the mortuary to get next of kin consent and liaise to allow the donation to happen. Once a post-mortem has taken place, the brain is transported to the brain bank. From here, one of our technicians will separate the brain into 2 halves so that the right half can be frozen and the left half can be preserved in a fixative. The reason for this is that different biochemical and molecular scientific techniques may need the tissue to be in a particular state. So by separating into halves, the most can be made from the valuable gift that somebody has given. The frozen half will be cut into slices that are 5 millimeters thick, from the front to the back of the brain, and then frozen very rapidly on -80 degrees Celsius brass plates to stop any ice crystals from forming. This preserves the tissue for use for a long period of time. The other half will be placed in a fixative called formalin for 3 weeks so that the tissue is then preserved. This half of the brain will then be examined closely by a neuropathologist at a weekly brain cut session with assistance from a research technician. I performed this job when I was a research technician and learnt so much about the anatomy of the brain and the subtle differences that can be observed with the eye to decipher the different neurodegenerative diseases. This fixed half of the brain is also cut into 5 millimeter slices. They are laid out and a preliminary diagnosis is given from examination by the neuropathologist. Most neurodegenerative diseases, and certainly many dementias, can only have a diagnosis confirmed at post-mortem due to large overlap between clinical symptoms and presentations between different types of dementia in life. This is why the first priority of the brain bank is to confirm diagnosis. This is then fed back to the family if they wish to know. From the fixed slices, small blocks of tissue are collected from the main and important regions of the brain for further preservation, such as areas affected in the diseases or areas of the brain that are important for brain function. These are then processed through a number of alcohols and chloroform to dehydrate the tissue and preserve it further before being embedded into paraffin wax. This process allows the tissue to be kept indefinitely. These wax blocks are then used to cut very thin sections of the brain tissue at 8 micrometers that are loaded onto glass microscope slides. Proteins of interest are then stained using a technique called immunohistochemistry, utilising antibodies against the protein you are staining to visualise these proteins under the microscope as shown in the image on the blog. In many neurodegenerative diseases, certain proteins accumulate into aggregates within the brain, and this can be observed using a microscope. A neuropathologist will examine the slides that have been stained for proteins affected in the various diseases and use consensus staging criteria set out by multiple research groups to determine which disease the person had. This will then be compared with the clinical notes for the patient, and a final definitive diagnosis will be given. If the family have requested to know the diagnosis, our brain bank nurse will feed this back to them. Once a diagnosis has been made, if consented for, the tissue can then be used for research purposes. Any researcher from the UK or worldwide can apply for the tissue via a tissue request, but a committee has to agree that it is an ethical use of the brain tissue and that the study is robust and well designed. Once this has been agreed, a material transfer agreement, a legal document, will be agreed to make sure that all aspects of the Human Tissue Act will be followed. A team of administrators and technicians at the Brain Bank administrate this and process the tissue request before it is sent out to the various research teams. A great deal of research has been propelled forward by the use of post-mortem human brain tissue, with many discoveries aiding better clinical diagnosis and understanding of disease processes being made. Needless to say, the gift of brain donation is not one that can be taken for granted and is the greatest gift to future generations that can be given. So when somebody asks me about what job I do, that is the message I like to get across.
The Brains for Dementia Research Project and network of brain banks across the UK are so vitally important to understanding dementia. We hope to have more blogs from Christina this year. In our next blog, we hear from Dr. Sam Moxon from the University of Manchester. Sam's work fascinates me. He works in 3D bioprinting and has provided some great blogs this year discussing his work. He's also interviewed some brilliant guests for the podcast. In this contribution, he asks the question, is tissue stiffness an overlooked aspect of dementia?
When you hear the word dementia, it's common to think about the symptoms from a few different angles. You might think of the mental side of dementia, loss of memory, confusion and hallucinations to name a few. It's possible that you also consider the physical aspects of the disease, like appetite and weight loss. Perhaps you'll also think of the biology that underlies the progression of dementia, the buildup of toxic proteins and subsequent loss of brain cells and matter. The one thing that you're not likely to think of is the mechanical side of dementia. It is not really widely publicised, but it is definitely something that is observed in dementia patients. So what do I mean by the mechanical effect of dementia? I'm referring to the mechanical properties of the brain, specifically how stiff it is. Every tissue in our body has a defined stiffness. Bone, for example, is classified as having high stiffness because it is very strong, firm, and can withstand high impact. It has to in order to be able to carry out its main functions of keeping us upright and protecting our much softer vital organs from impact damage. In contrast, the brain is an extremely soft and fragile tissue. That's why our skulls are so thick. We need to protect our brains from damage. Tissue stiffness is very closely controlled in our bodies, and the cells embedded within our tissues are as much in control of tissue stiffness as they are controlled by it. Stiffness is one of the many properties that in our bodies is regulated by an intricate and elegant balance of homeostasis. Any healthy patient should be exhibiting tissue stiffnesses within the normal range. Certain diseases have, however, been shown to correlate with a change in tissue stiffness. Many cancers, for example, result in an increased tissue stiffness as the tumour cells grow and remodel their environment to become more tumour-friendly. In breast cancers, it's common to see fibres of collagen become dense and more aligned, and that results in an increase in breast tissue stiffness. Interestingly, medical evidence is now also pointing towards dementia as being another healthcare issue that results in changes in tissue stiffness. However, the picture is a little bit more complex than as simple as the stiffness is always going either up or down. It appears it depends on what dementia-causing disease is persistent in the patient. In Alzheimer's, for example, the brain is often seen to become significantly softer than normal. That's perhaps not surprising given that Alzheimer's results in the death and loss of brain cells and tissue. You'd expect the brain to become mechanically weaker as a result. Conversely, in dementias with an integral vascular complication, many studies have shown that the blood vessels within the brain actually become stiffer as they become more hypertensive. Either way, these changes in stiffness could provide ways of diagnosing dementias earlier than we can now. Normally, a patient is not diagnosed until the neurodegenerative mechanisms playing out in the brains become advanced enough to manifest as physical or mental symptoms. At this point, a considerable portion of the brain has already been lost. Being able to screen for more subtle changes in brain tissue stiffness could alert medical professionals to early signs of dementia progression, allowing therapies to be administered before large-scale damage is done. This would have a major impact on the lives of dementia patients. So I guess the big question is, how do we go about screening for it? Normally in a lab, if you want to probe the stiffness of a material, you have a range of equipment to use from rheometers, compression testers, and different types of microscopes. However, you can't really cut someone's head open and take a sample of brain tissue to measure the stiffness and determine its health. It's a bit counterintuitive. It turns out the answer lies in something that is used in hospitals every day. Magnetic resonance imaging, or MRI, is commonly used to examine tissue health and is a key diagnosis tool for dementia. If MRI is combined with low-frequency vibrations, it allows practitioners to get an elastic map of a tissue. The process is called magnetic resonance elastography, or MRE, and it can detect regional changes in brain stiffness without having to cut a patient open. It's a powerful tool and could have a big role to play in improving the speed and accuracy with which we diagnose and treat cognitive impairment. I'm definitely not saying we should drop everything else and just focus on this, but with so many questions still remaining about how we can better understand and treat dementia, why not use all the tools we have? Tissue stiffness changes are one of many manifestations of dementia. It is good to see it being given the consideration it warrants in the ongoing discussion about how we can fight to eradicate neurodegeneration for good.
Sam is brilliant at looking at things holistically and making connections. Do take a look at his other blogs. Our third blog comes from Dr. Yvonne Couch, who I'm sure you know is an ARUK Research Fellow at the University of Oxford. It was first shared on the 18th of June. This is just one of many fascinating blogs Yvonne has provided in her own unique style, which I love. She always provides some of the history to go with the science, which makes them really engaging. In this article, she talks about the science behind extracellular vesicles.
The hunt for tiny messengers. Science time! Today we're going to talk about extracellular vesicles. You know, those things that dude down the corridor works on that you don't really believe are a thing. We'll go the semi-patronising route I took with the stroke chat, and I'll tell you a little bit about the history of the field, a little bit about what extracellular vesicles are, and a little bit about why they're interesting. We're going to start in the 40s, where you could get away with writing a series of 30 papers on basically the same thing, each with only 2 beautifully hand-drawn graphs and 1 meticulous table in. There were these 2 chaps, Chargaff and West, who were a biochemist and a medic respectively. They were trying to figure out how all the disparate components of blood came together to make a clot, by spinning down and separating all the components to see what they did. In 1936, they began a series of papers called Studies on the Chemistry of Blood Coagulation. And paper 19 of the series is what we think might be the start of the field of extracellular vesicle research. They found that the addition of the high-speed sediment to the supernatant plasma brought about a very considerable shortening of the clotting time. Basically, in the truly broadest sense, don't hate me, extracellular vesicle people, if you spin down blood with anticoagulant in, you get plasma. If you spin down that plasma, you get extracellular vesicles. And a load of other stuff, but we'll get into that on a later occasion. In the next paper in the series, they took plasma from a normal adult, a haemophiliac, and a female with what is described as a clotting disorder, with no apparent interest in which one. You can tell this is the 30s because the details are sparse and the N is 3. They timed how long it took for clots to form in all of these patients and found, no surprise, the haemophiliac and the female with the clotting disorder didn't clot all that quickly. Then they took the sediment they found earlier, the one I said is probably the extracellular vesicle fraction, and applied it to these patients' bloods, and found that the time to clot was much quicker. Whilst they said at the time that this fraction probably includes, in addition to the thromboplastic agent, a variety of minute breakdown products of blood corpuscles, they did not call them extracellular vesicles or explore them any further. Now, between the 40s and the 80s, there is a ton of literature that never really went anywhere. People seem to have found extracellular vesicles in all sorts of places and not pursued them as anything exciting or novel. If you're interested and patient, there's a history of extracellular vesicle review due out sometime soon, care of yours truly and a whole bunch of much more eminent extracellular vesicle people. But where the field really started to come into its own was in the 1980s. Rose Johnstone and Philip Stahl were looking at receptor trafficking. They both published papers in 1983 on the transferrin receptor. In these papers, they had found the receptor on vesicles within multivesicular bodies and had found these vesicles were released by exocytosis. Whilst the term exosome cannot be attributed to either Johnstone or Stahl, but rather to Eberhard Trams of Ursula Heiner's lab, Rose Johnstone was the first to officially describe exosomes. She hailed them as lipoprotein structures with a phospholipid composition characteristic of red cell membranes. This leads us neatly to modern classification systems and the sticky mess therein. Most people will have heard of exosomes, but it's now considered a rather old-school term, and the more widely accepted one is extracellular vesicles, or EVs, as I will now call them because it's less of a mouthful. EVs can be broadly classified into two camps according to their biogenesis. Large EVs, usually more than 150 nanometers, are shed from the cell surface. These used to be called microvesicles or microparticles. Small EVs, usually less than 150 nanometers, are formed by invagination of the cell membrane. They're stored in multivesicular bodies and released by exocytosis. These used to be called exosomes. The problem here is that there is a lot of overlap in sizes and some shared markers between the different classes. ICEV, the International Society for Extracellular Vesicles, has published some great position papers on the issue, so feel free to go and peruse should you wish to know more. That covers what they are, but what do they do? This is where we run into the EVs aren't a thing issue. Despite her initial discovery of them and her continued research into EVs for a number of decades, this problem might have been Rose Johnstone's fault. In a paper in the early 90s, she says, "The observations with the transferrin binding are consistent with the conclusion that exosome formation may be a major route by which maturing cells selectively lose obsolete plasma membrane functions." This led many researchers who came after her to believe that EVs were just a way for the cells to shed junk proteins. The EVs were nothing more than cellular debris with no further function. It was the mid-90s when papers began to show that EVs were actually functional. One paper which was particularly important was by Grassa Raposo and her colleagues, who demonstrated that EVs from immune cells are capable of presenting antigen. This paper has been described as a watershed moment, catapulting the potential of EVs to be harnessed as therapy. Just over 2 decades later, this is beginning to become a reality. EVs are used in all facets of disease. There are FDA-approved diagnostic tools using EVs, and companies manipulating their chemistry to use them as therapy. But my interest has always been function. Where do they come from and what do they do? And how do they do what they're doing? Let's think about them in the context of dementia, otherwise I feel like I'll lose you to my history lesson. Although, let's be honest, it's still going to be a bit of a history lesson. A search for exosome and dementia brings up papers starting around 2006, demonstrating that EVs are capable of acting as a vector for amyloid beta, that they act as release mechanisms to shed amyloid from the cell, and that this EV-associated amyloid ends up within plaques. But a search for microparticle or microvesicle and dementia brings up much earlier papers from the late 80s showing very similar phenomena. There is now considerable evidence that in a number of neurodegenerative diseases, EVs can propagate misfolded protein in a sort of broken version of the game telephone, but with cells. We know that if we inhibit the release of EVs, we can slow the propagation of disease. We also know that other cells within the brain can take up these EVs, cells like microglia and astrocytes. These cells can become activated, starting to produce reactive oxygen species and reactive nitrogen species, and causing neuronal death by what one of my colleagues wonderfully describes as chemical-friendly fire. EVs are capable of crossing the blood-brain barrier, and the hunt is now on for brain-derived EVs in the blood. Because EVs are so prevalent in the blood, looking for them there in pathology is often described as a liquid biopsy. This is increasingly becoming of interest to those in the field of CNS disease, where catching things like dementia early, before it becomes debilitating, is vital. Biopsies from the brains of otherwise healthy people tend to be frowned upon, but a simple blood test in asymptomatic populations might not be unreasonable and might allow us to jump in early and start something prophylactically. So EVs have the potential to propagate disease, to diagnose disease, and maybe even to be used as therapy in disease. And in challenging diseases like dementia, all of those things could prove important. I think we've established that they're definitely a thing. So if you have time, go down the corridor and chat to that dude about them. You might learn something fascinating.
Did that inspire you to go down the corridor and talk to the dude you never met? Yvonne has just recorded a brilliant podcast exploring the effects of space travel on the brain. This will come out in March to coincide with Mars Day, so make a note in your diaries. The final blog in this show comes from our newest staff blogger, the awesome Dr. Kamar Ameen-Ali from the University of Glasgow. Although I gather congratulations are in order, as she's about to make a move back to Teesside. First published back in September, this blog is titled, Why Does Brain Injury Increase the Risk of Dementia?
Experiencing a traumatic brain injury, or TBI, is the strongest modifiable risk factor for developing dementia, but we don't know what happens in the brain after injury that makes someone more vulnerable to developing a neurodegenerative disease that ultimately leads to dementia. In this blog, I'm going to be introducing you to my research area and asking the question, why does brain injury increase the risk of dementia? To understand what a TBI actually is, it's probably best to first go over some terms. Following a head trauma, the level of consciousness can be assessed using the Glasgow Coma Scale, or GCS, which is a commonly used scoring method which measures eye, verbal and motor function. The GCS score gives an indication of the level of TBI severity, which ranges from mild, also known as concussion, to moderate and then to severe. A single TBI might occur because of an accident or assault, for example, and can vary in terms of severity. Head injury in sport has been receiving a lot of media attention recently and can be a useful context to help us understand the effects of mild repetitive TBI, which can occur from experiencing multiple concussions in some contact sports or from repetitive impacts from heading a football throughout a player's career, for example. Now we've established the different types and severities of TBI, let's try and understand why it is a risk factor for dementia. TBI is known as a modifiable risk factor, which means that it is considered to be a risk which can be potentially controlled and minimised just like the other 11 modifiable risk factors, which were outlined in the Lancet Commission on Dementia Prevention, Intervention and Care, updated last year, and which also includes, for example, smoking, physical inactivity, and hypertension. This is in contrast to risk factors such as genetics and aging, which are non-modifiable. Therefore, the key to understanding dementia risk is to minimize the modifiable risk factors as much as possible, which includes potential exposure to head injury. To explore why TBI increases the risk of dementia, we need to ask the question whether the risk for some dementia-related neurodegenerative diseases is greater than others. The neurodegenerative disease chronic traumatic encephalopathy, or CTE, has for a long time been associated with experiencing multiple head impacts, with researchers first describing the range of associated pathologies in former boxers. However, in the last 20 years, CTE has also been reported in other former contact sport athletes, from football, rugby, and American football most notably. So CTE is a neurodegenerative disease which results in dementia, but is it exclusive to athletes who may have been exposed to repetitive head impacts or concussions throughout their careers? Not quite. Research has shown that CTE can result from different types of TBI exposures, which means it is not exclusively a result of repetitive head impacts that may be typically associated with contact sports. We also know that CTE is not the only dementia-related brain disease that is associated with TBI, as the risk of Alzheimer's disease, or AD, and Lewy body dementia, for example, are also increased following brain injury. Clinically, CTE and AD might look quite similar in terms of how the dementia symptoms present, which makes CTE difficult to diagnose in life. In fact, there is currently no consensus criteria for clinically diagnosing CTE, and it is only through examining brain pathology post-mortem that we can establish what might be the primary pathology driving the dementia syndrome. For both CTE and AD, we see an accumulation of certain proteins in the brain, and it is the pattern and distribution of these pathologies that allows us to distinguish between these two neurodegenerative diseases. We've established that TBI, whether it is single or repetitive head impacts, increases the risk of dementia-related neurodegenerative diseases more broadly, not just CTE. But we still haven't answered the question, why does brain injury increase the risk of dementia? To answer the question, it might be helpful to imagine the black box metaphor, where the inputs and the outputs of a system are known, but how the actual system works is unknown. We can imagine brain injury as the input and neurodegenerative disease pathology as the potential output. The black box in between the input and the output represents the lifelong neuropathological changes which occur in brain injury survivors if they go on to develop dementia. Our aim is to try and work out what is happening in that black box, as therein lies the answer to our question of why and how brain injury increases the risk of dementia. To give you an insight into the steady progress we're making in trying to answer this question, from previous research we know that the parts of brain cells which carry electrical impulses, the axons, become damaged after TBI across all severities. An amyloid precursor protein may accumulate in these axons, ultimately resulting in the beta amyloid plaques, which are characteristic of some neurodegenerative diseases like AD and CTE. My interest is specifically in how neuroinflammation might be the driver of neurodegeneration following TBI exposure. Microglia are immune cells in the brain with a diverse and dynamic range of functions, and they are activated as part of the neuroinflammatory response. I'm investigating whether chronic activation of microglia after brain injury leads to the progression of neurodegenerative disease pathology. If there is a link between neuroinflammation and other pathological changes following TBI, we will not only be able to identify therapeutic targets, which will minimize brain injury as a risk factor for dementia, but we will also have greater insight into the processes involved in the development and progression of dementia-related neurodegenerative diseases that are not linked to a history of TBI.
That's such an important line of inquiry, and brilliant to see the FA and other sporting bodies taking it seriously. That's all we've got time for today. We'll be back tomorrow with more great blogs from our 2021 archive.
Thank you for listening. Join the Dementia Research bloggers and share your own views.